Hi everyone. This work is called 6 Candidates Suffice to Win a Voter Majority. This is joint work with 4 wonderful people, Moses Charikar, Alex Lassota, Adrian Vetta, and Kangning Wang. So this work has to do with elections, and so the typical setup is that we have some voters and we have some candidates, and the voters have some ranked preferences over the candidates. So for example, this table here might represent the results of an election that has 10 voters and 5 candidates. And so the top row of this table represents the voters' first choices, and the last row represents the voters' last choices. So for example, voter 1's favorite candidate is candidate 4, and then their second favorite would be candidate 5, and so on, and their least favorite candidate would be candidate 2. And so the question that we have faced with these elections, and the central question of this broader area called social choice theory, is how do we go about choosing the best or the most broadly appealing candidate? The reason why we're interested in studying this question is that elections, this idea of voters choosing from candidates, can model quite a wide variety of decisions that groups of people make together. So probably the most prominent example is in political democracy, where a group of constituents chooses their representatives. But you can also imagine an organization choosing who to hire, like at a university or a company, or a group of judges choosing winners of a prize. There are also very everyday decisions, like a group of friends choosing where to eat, or maybe what to eat when they get there, or choosing what board game to play together, or for their book clubs or their movie nights. All these kinds of things, once you start seeing them as elections, it becomes hard to unsee. There's also been an explosion of recent work building connections between social choice theory and artificial intelligence because of the way that human preferences are used these days in the training and fine-tuning of language models. And so here is just a collection of work that's happened in 2024. So, returning to this question of how do we go about choosing the most broadly appealing candidate, one reasonable principle that we might strive for is something called majority rule. So for example, if a majority of voters prefers candidate A over candidate B, then we probably shouldn't choose B instead of A. That seems like an awfully undemocratic thing to do. But it turns out there's a problem with this, which is something called Condorcet's paradox, which dates back to around the French Revolution. So it turns out that there are elections where no matter which winner you pick, a majority of the voters will prefer one of the other candidates. And so the simplest example of this is this following election with 3 voters and 3 candidates, where the voters their preferences follow a sort of cyclical ordering. So the first voter has the preference 1, 2, 3, and the second voter has the preference 2, 3, 1, and the third voter has the preference 3, 1, 2. And so if we choose candidate 1 in this election, then a majority of voters, 2 out of 3, would tell us that they prefer candidate 3. But if we choose candidate 3, then 2 out of 3 would prefer candidate 2. And finally, if we would choose candidate 2, then 2 out of 3 voters would prefer candidate 1. And so this paradox is the first in a long line of impossibility results in social choice theory. Maybe the most famous one is Arrow's theorem. But even just this simple paradox is a lot less innocent than it might look. So it turns out that there are actually elections where no matter which winner you pick, 99% of the voters will prefer one of the other candidates. And so the idea is just to take this same cyclical example, but then blow up the size of the cycle. And so here is an election with 10 voters and 10 candidates, where their preferences follow the same kind of cyclical ordering. And so if we choose an arbitrary candidate here, say candidate 5, then all but 9 out of the 10 voters will tell us that they prefer candidate 4 over candidate 5. And so this might seem like a bit of a contrived example, but it points to a kind of unsettling possibility that no matter what choice we make, basically everyone will be unhappy. And so what can we do about this? Well, we need to relax the problem. So can we make the goal a little bit easier and alleviate the paradox? So one idea is, what if we allow for multiple winners, called a committee in the literature? And so if we look at these half of voters on the right who are particularly unhappy with candidate 5, we can make them a lot happier if we also include candidate 10. And so now we find that there's no longer some other candidate that a majority of voters prefers over both candidate 5 and 10. So at most 4 out of 10, 40% would prefer candidate 4, and similarly 40% would prefer candidate 9. But there's no other candidate that a majority of voters could get behind and say, hey, why are you choosing these two candidates? Clearly this choice is a better choice. And so you might ask, are we cheating by allowing us to choose multiple winners? Well, it turns out that actually this idea of committee selection shows up in a lot of these different decision-making problems that we discussed earlier. So for example, it can be natural to have multiple winners for grants or for fellowships or accepting papers at a conference. You might make multiple hires at once, or when you're out to dinner with your friends, you probably order more than one dish for everybody. And there's also been a lot of work in the political setting about using multi-winner districts to get at something like proportional representation. If you're curious, here's an article from the New York Times from a few months ago where they discuss the ways in which people think about this in the zeitgeist. You can also think of committee selection as a kind of pruning step, where first you want to choose a short list of candidates, and then you might do something with that later on. For example, choosing nominees for a prize, or a group of people to interview for a position before hiring one, or again in the political setting with primaries or runoffs. And so with all this in mind, here's the problem that we'll study. We saw that with Condorcet's paradox, it's possible that no matter what winner we choose, a majority might prefer one of the other candidates. And so the question is, what if we can choose multiple winners? Can we choose a set of K winners such that less than 50% of the voters prefer any of the other candidates over all of the winners? So if we compare the K candidates we choose against any of the other candidates, the fraction of voters that prefers the other candidate over all of our K is less than 1/2. And so this notion was originally defined by Elkin, Lang, and Safadine in 2011, and they called these sets Condorcet winning sets. Naturally, we would like to do this with small sets. So of course we could just choose all of the candidates, and this would be a Condorcet winning set. But can we do this without having to choose too many candidates, Can we choose a set of candidates to interview such that we don't have to interview everybody? And similarly, you could generalize this 50% fraction to some arbitrary alpha, and you could ask for each value of K, what's the best or smallest alpha that we can achieve? One thing I love about this question is it feels like a really natural and simple question, something that you could imagine Condorcet asking himself in the 18th century. And yet, the tools that we use to tackle it would actually not have been available to Condorcet. So the workhorses of our approach are game theory and the probabilistic method, and we also build on some very recent work on something called approximately stable committee selection by my co-author Kangning and some of his collaborators, Cheng, Jiang, and Munagala. But before getting into our work, let's see what was previously known about this problem. So we saw that Condorcet's paradox can be thought of as showing that K equals 1 does not suffice. And so naturally, what happens if we look at K equals 2? And so it turns out that actually 2 candidates also does not suffice. And so this was already shown in this first paper by Elkin, Lang, and Safadine. And so here's how their example works. And so the idea is that instead of just having one cycle, we're going to take 2 cycles and multiply them together. And so here, if you just squint your eyes, these boxes represent a 3 cycle. And then what we're going to do is we're going to replace each of these boxes with a large cycle of candidates. And so we replace the box 1 with candidates 1 through 5 in a cycle, and then the same kind of thing with candidate 2, and the same kind of thing with candidate 3. So now we have this election with 15 voters and 15 candidates. That's like the product of 2 cycles. And I claim that if we choose any 2 candidates here, then a majority will prefer one of the other candidates over both of the 2 candidates that we chose. And so, for example, if we choose 2 that are within the same inner cycle, like candidate 3 and 5 here in the green cycle, then we can kind of squint our eyes, and it looks like we just chose one candidate from the 3 cycle, the kind of outer cycle. And so we can see that if we choose a candidate from the preceding cycle, then this candidate will be preferred over both 3 and 5 for 2/3 of the voters, 10 out of 15. On the other hand, if we choose two candidates from different inner cycles, like candidates 5 and 10 here, from the green and orange cycles, then one of these two candidates is the better of the two for 2/3 of the voters. So that's candidate 5 here. And so now if we appeal to the inner cycle of this candidate, then the candidate just preceding, candidate 4 now, is more preferred over candidate 5 for almost all the voters. And so they'll be preferred over both 5 and 10 for now 8 out of 15 voters. And more generally, if we make this 5 cycle even larger, then the fraction of voters that would prefer candidate 4 over both 5 and 10 would get arbitrarily close to 2/3. And more generally, if instead of a 3 cycle you use a k+1 cycle, you'll find that any k winners you choose, one of the other candidates will be preferred by arbitrarily close to 2 over k+1 fraction of voters. And so for k equals 2, this is 2/3, but actually for k equals 3, this could still be 1/2. So it could be that 3 candidates is enough to win a majority of voters based on this example. And let me point out that there's been subsequent work that's found other kinds of counterexamples, some using combinatorial designs and some using computer search, but mysteriously, none of these have come up with any examples that require more than 3 candidates to win a majority. On the other hand, it's not too hard to show that you can get k to be logarithmic in the total number of candidates. And so the idea is just a simple greedy algorithm. You can argue that the candidate that wins the most pairwise majority votes, that beats the most other candidates, has to beat at least half of the other candidates. And so all you do is add this candidate to your set, remove the candidates that it beats, and then recurse on the remaining candidates. And so each time you do this, you cut the number of candidates in half, and so you end up with a set that's logarithmic in the total number of candidates. This is really just the fact that tournament graphs have dominating sets of logarithmic size. And so the question is, what's the right answer between 3 and log m? I can tell you that when Adrian and Alex first told me about this problem, I thought for sure that the right answer should be log m. It's the right answer for dominating sets, and I couldn't see why this problem should really be so different. But it turns out that I was wrong, and so we show that in any election, regardless of the number of voters, or the number of candidates, or their preferences, you can always choose at most 6 winners, such that less than 50% of the voters prefer any alternative candidate. More generally, if you can choose k winners, then you can satisfy all but alpha fraction of the voters, so long as alpha and k satisfy this inequality. This might be a little bit hard to parse, but you can think of alpha, this is just some lower bound on alpha, so as long as alpha is sufficiently large, then we can do this. And if you compare this to the negative results, then this is sort of right up to this 1 minus ln alpha factor here. Maybe it's a little bit easier to see with a picture, and so here is a plot where the blue points are our positive results, and the red line here is the negative result. And so let me point out just a few interesting points here. And so you can see that actually even with just 2 candidates, you can avoid this nightmare situation where almost all of your voters are unhappy. So you can satisfy all but 80% of your voters roughly. If you go further out, then you can see that we cross a threshold of 1/2 between 5 and 6 here. And if you go even further out, like the number of Oscar Best Picture nominees, then you can find that you can satisfy all but 1/3 of the voters. An interesting fact is that actually before 2010, the number of Oscar Best Picture nominees was 5, which you can see is a lot worse. And so you can ask what happened in 2009. And so it turns out that people were really unhappy that The Dark Knight wasn't nominated for Best Picture, and also that Wall-E was also not nominated for Best Picture, which in hindsight were 2 really great movies. And so it's essentially a large fraction of the unhappy movie-going public got them to change the rules. I'll have more to say about the proof at the end, but I thought it would be more fun to take a little bit of a digression and tell you about something completely different. So imagine I present you with the following dice game. We have these 4 dice, and you and me, we're each going to pick one of these dice, and then roll the dice, and whoever gets the higher roll wins. And so the question is, if you get to pick first, which of these dice should you choose? Now, it might look like you have to do a bunch of horrible arithmetic to figure this out, but it turns out there's actually a kind of nice way of thinking about it. And so if you're kind of boring, you might go with this blue die, which always gives you a 3. But it turns out that's actually not such a good choice, because this red die gives you a 4 2/3 of the time. And so this red die will beat the blue die 2/3 of the time. And so now what if you choose the red die? Well, it turns out that's also not such a good choice because of the green die. And so the green die, half the time, will give you a 5, and that'll automatically beat the red die. And there's also a little bit of change for when the green die gives you a 1 and the red die gives you a 0. And so again, the green die, turns out, will beat the red die 2/3 of the time. But now, the purple die will beat the green die because of the same argument in reverse. So half the time, the green die gives a 1 and automatically loses to the purple die. And then there's again some change for when the purple is a 6 and the green is a 5. And finally, this purple die actually loses to the green die because 2/3 of the time, the purple die gives you a 2. And so that's automatically going to lose to the blue die, which is always a 3. And so it turns out there's actually no good choice of dice. And so these are called intransitive dice. And these particular dice were designed by a Stanford statistician named Bradley Efron. Let me mention that there's been a lot of work on intransitive dice by mathematicians, including one polymath project some years ago. They've also been a popular topic in a lot of general audience math literature. And so probably the origin of all of this is a Scientific American article by Martin Gardner, where he popularized these Efron dice that I mentioned on the previous slide. And there's a kind of funny anecdote that often goes along with these articles, which is that apparently Warren Buffett is like a big fan of these dice, and he has a set of them and likes to use them to trick his friends into paying for lunch. And there's a story that goes that one time he was trying to do this with Bill Gates, and so he poses him this dice game and says, because I'm such a nice host, I'll let you pick first. And then Bill takes a look at the dice and spends a couple minutes doing some math, and he says, actually, maybe you should pick first. And so you might look at this game and say that now that you know the trick, it's kind of no fun. It's always rigged against the person who chooses first. And so what if we give the first chooser a bit of a leg up and allow them to choose multiple dice and then let them take the best roll out of all of the dice? And so a question is, can this game still be rigged? So maybe you might see where this is going, and so it turns out that actually this was all a voting problem in disguise. So if you think of the dice as candidates, and then you think about each point in your sample space as a voter. So like each roll of the dice is a voter. And then the order of the dice in these rolls as the preferences. So for example, this voter corresponding to this roll would have the preference green over blue over purple over red. Then the phenomenon that every dice loses to one of the other dice more than 50% of the time is exactly the same phenomenon as every candidate losing to another candidate for a majority of voters. And so actually, these intransitive dice were just an example of Condorcet's paradox all along, with some very special independence in the way that the voters' preferences work. And so analogously, there's a dice version of our result, which is that with any arbitrary dice, even if the dice can be arbitrarily correlated with each other, 6 dice is enough to win an advantage in this game. And it turns out this is actually an equivalent way to think of our result, and so if you prefer this version, you're welcome to think about it this way. So now I'd like to say a little bit about how the proof works. To give you a high-level overview, here's my one-slide vision board of how the proof works. So in the first stage, the idea is that actually the randomized version of this problem, where you can choose a distribution over committees instead of just a single committee, is actually a much easier version of the problem. And the idea is that you can just hit it with a game theory hammer because it's a lot easier to understand how to play games where you can randomize over the strategies rather than when you have to deterministically choose the strategies. Next, the idea is to use this good distribution over committees as a kind of measuring stick. So instead of comparing committees and candidates against each other directly, we're going to compare them against this good distribution. And so there's this nice visual way of thinking about that comparison, which turns it into comparing some certain areas. And so finally, what we eventually want to show is that there's some committee that has a large area, and we can do that by just showing that a random committee drawn from the distribution actually has large area in expectation. And then we'll be done. And so let's dive into this first part of the proof. Ideally, what we would like to show is that we can always choose a committee S of size k, such that for any alternative A, at most 2 over k plus 1 fraction of the voters prefers candidate A over all of the candidates in S. And so this would resolve the problem outright and match the negative results that we saw earlier. If you prefer in mathematical notation, this is what it would look like. And so this here is some notation for the fraction of voters that prefers candidate A over all the candidates in S. And so the question is, what if we can randomize and choose a distribution over committees instead of just one committee? And so these earlier works that I mentioned were able to construct something called a stable lottery, which is a distribution over committees, such that for any alternative A, in expectation, at most 1 over k plus 1 fraction of the voters prefer A over a committee drawn from this distribution. And so, importantly, we're actually able to get a better result here with distribution than we could hope to get without a distribution. We can get 1 over k plus 1 versus 2 over k plus 1. And so the proof is just a very slick application of von Neumann's minimax theorem. And so the idea is that you can think of this as a kind of game where I'll choose a distribution over committees, and then seeing my distribution, you can adversarially choose a candidate A, and then we'll draw a committee from my distribution and then have the voters compare. So we look at the fraction of voters that prefers your candidate over all of my candidates. You can imagine, for instance, that I'll pay you $1 for each voter that has that preference. And now the minimax theorem basically lets us flip the script. And so instead, you can think of this as equivalent to a game where you first choose an adversarial distribution over candidates, and then seeing your distribution, I can choose a committee S, and then we draw from your distribution and have the voters compare. But now, the key thing is that I can use your distribution to construct my committee. And so all you do to choose S is sample k times from the adversary's distribution. And so each voter now is basically seeing k plus 1 samples from some fixed distribution, and so the probability that they like your sample A more than my k samples S is exactly 1 over k plus 1. Mathematically, this is what the proof would look like if you want to read through it more formally. Now let's move on to the second stage of the proof, where we'll create this measuring stick. So the intuition is that we're going to create a kind of visual representation of this distribution delta over committees and the voters' preferences over committees and candidates. And the way it's going to work is that more preferred candidates and committees are going to be higher up in the picture, and at the same time, all the candidates are going to be low, and the committees are going to be typically high up in the picture. And so this is going to be the source of the contradiction. The typical committee is then going to be higher up than all of the candidates and therefore more preferred, and that'll be exactly what we want. And so in a little bit more detail, we're going to have a 1-by-1 box, and this box is going to have a column corresponding to each voter. So let's focus on just one voter's column. And so this column consists of a stack of blocks, and so each of these blocks corresponds to a committee. So every committee gets a block in this column, and the height given to a given committee is exactly its probability mass in this distribution delta. So there might be some blocks that have no thickness if they're not given any probability mass in the distribution, but the point is that because the total mass is 1, that means that these blocks are going to fill up this height 1 of the column. And then these blocks are going to be ordered in a very particular way. They're going to be ordered by this voter's favorite candidate in the committee. And so at the very top will be the committees that have this voter's very favorite candidate, and then will be the committees that have this voter's second favorite candidate, and so on and so forth. Finally, the last thing is that individual candidates will be slotted in between the blocks, right above the committees that have less preferred candidates. And so you can think of this as where these candidates would be if you thought of them as just singleton committees. So it might be a little bit easier to understand this with an example. So let's imagine that we have a distribution delta which randomizes over these 4 committees, which are just pairs of candidates. And delta gives them probability mass 0.1, 0.2, 0.3, and 0.4. And now let's look at a voter who prefers A over B over C over D, and let's look at how their column will stack up. So at the top, we'll have the committees that include this voter's favorite candidate, and so that's AB and AC, and the voter will break the tie in favor of AB because they prefer B over C. The next will be the committees that have this voter's second favorite candidate, so that'll be BC, and then at the bottom we have CD. Now let's look at where the candidates are, and so candidate A will be above all of the committees that only consist of candidates that are lower ranked than A. And so those are the committees that only have B, C, and D, and so that's right above over here. And then similarly, B will just be above CD, and C and D will just be at the very bottom at height 0. Another helpful way to think about how these are stacked is you can imagine encoding each of these committees and candidates in binary according to this voter's preference. And so AB corresponds to 1, 1, and then 0, 0. AC corresponds to 1, 0, 1, 0, and so on. And so the order of these committees and candidates is just exactly the order of these binary numbers. Finally, let me point out that the height at which a candidate sits, say candidate A here, corresponds exactly to the probability that this voter prefers A over a committee S drawn from delta, because this probability is exactly the total probability mass given to committees that consist of candidates worse than A, and those are exactly the committees that are below A in this column. Now, with this observation, it turns out that if we look at this key property of delta, which is that for all candidates A, the expected fraction of voters that prefer A over a committee S drawn from delta is at most 1 over k plus 1. What this translates to in the picture is that the area underneath A is at most 1 over k plus 1. So this area corresponds exactly to this expected fraction of voters that prefers A over S drawn from delta. And so this is the sense in which all of the candidates are low. So if you imagine that K is like 100 or something, then all the candidates have at most like 1% of this box underneath them. And so they're really just scraping the bottom of this square. And so next, what we want to show is that some committee is high up, too high up for the majority to prefer any candidate over this committee. And so what exactly would this look like? So let's focus on one committee, and let's sort the voters by the height that this committee has for the voters. And so how could a candidate be preferred over this committee for a majority of voters while having very small area? The most efficient way for a candidate to beat this committee would be to be just above S for the bottom half of the voters, and then drop down to height 0 afterwards. And so then, if we look at this area for the bottom half of voters, if this area is bigger than 1 over k plus 1, then we have a contradiction. Then it can't be possible for any candidate to beat this committee for a majority of voters, because then that candidate would have to have area that's too large. And so this is the sense in which a committee can be too high for a majority to prefer it, to prefer any other candidate over this committee. So how do we find a committee that satisfies this, that's too high? The idea is to show that a random committee drawn from the distribution delta is too high in expectation. The key intuition is that from each voter's perspective, sampling from this distribution is like throwing a dart at the column that lands at a uniformly random height and seeing which committee's block it lands in. And so one easy argument you can make is that if you look at the height 1/4, then in expectation, 3/4 of these darts land above height 1/4. And so that means, by the probabilistic method, there has to exist some committee S that has height at least 1/4 for at least 3/4 fraction of the voters. And so if we take a committee like this, we can argue that if some candidate beats this committee for a majority of voters, then the area under that candidate has to be at least 1/16. It has to capture this 1/4 by 1/4 square. And so that means that we'll get a contradiction as long as k is at least 15. If k is at least 15, then this area is bigger than 1 over k plus 1. And so that's enough to show that 15 candidates suffices. To give a hint at how you could get a stronger argument, you can show that if these darts were actually completely independent, then you'd expect their shape to look kind of like a slope 1 line. And so experimentally, this is what it looks like if you take, 1,000 uniformly random samples and then sort them. And so if you did get this kind of shape, then you could show that if a candidate beats this committee for a majority of voters, then now it has to capture this isosceles triangle, which has area at least 1/8, and that would be enough to show that 7 candidates suffice, which is very nearly the way to 6. So it turns out that actually making this argument work is a little bit tricky, but you can actually make this work. And you need a couple more ideas to get to 6, but I'll let you check out the paper if you're interested in learning more. Finally, I'd like to conclude with some big picture reflections. I think that because of the role that elections play in our culture, with them being so tied to politics and politics being so fraught, we can have a lot of baggage around elections that can really color our perspectives. For example, sometimes when I talk about voting with randomness, people can get a little bit uneasy, because the idea of making a really big decision with a coin flip is really scary, and I think that's a completely reasonable reaction. Maybe one answer to this is something that we saw earlier, which is that elections are a lot more than politics, and because there's such a wide range of applications, maybe we should keep an open mind and study an equally wide range of questions. But another perspective is to think of elections as just another kind of fundamental mathematical object, akin to graphs and partially ordered sets. All an election is a distribution over orders, and so maybe when we see a bunch of orders like the numbers on these dice, it should be our first instinct to think about them in terms of elections. And so I think it's exciting to take a page from the mathematicians and study elections deeply and thoroughly with a kind of unencumbered curiosity. And I think it's somewhat surprising how many fundamental questions, like the ones in this talk, that we don't yet have complete answers to. And so with that, I'll conclude with some takeaways. Thank you very much.